Okay, we're going to go on to the derivation of the Fab Five, the famous fabulous 5 equations for kinematics. First one we're going to look at is v2 equals v1 plus at. We start with the idea that acceleration is equal to dv dt. Using separation of variable technique for integration, I'm going to move dt to the other side. So I have dv equals a dt. We'll take the integral of both sides, so the integral of dv that equals the integral of a dt. Well, a is a constant here, so the integral of this side here, we pull the a out in front. We're actually taking the integral of dt, which is just t, so we end up with at, and then we have the integral of dv just becoming v. So v equals at plus the constant integration c. Well, we figure out the constant of integration by putting in 0 for time. We find out that v is equal to c. And that's a special v, that means the beginning velocity. So our constant of integration, c, is equal to v naught. So our equation then is v equals v naught plus at. Now applying it as a definite integral then, the left side would be v under a definite integral of v naught to v final equals a under the definite integral for t, subbing in t1 to t2. So doing so, this becomes v final minus v initial equals a t2 minus t1. Moving this to the other side, our first Fab 5 equation then is v final equals v initial plus at. What does t actually represent? T really means the change in time for the entire duration. So v final means the final velocity after that time duration, and v initial means the beginning velocity of that time duration. And last year we would have said it v2 equals v1 plus at. This year we're going to call it v final and v initial. Moving on to our second famous equation, x equals v naught t plus 1/2 at squared. We start with the idea that v is equal to dx dt. Well, we have in our previous equation v equals v naught plus at. Well, v is a variable, v naught is a constant. So what do we have then? We'll plug in dx dt for v. So dx dt equals v naught plus at. Remembering v naught is actually the beginning velocity. So that really is the constant of integration. We're going to apply separation of variable technique again. I'm going to multiply dt to the other side. So we have then the integral of dx equals the integral of v naught dt, because I multiplied dt there, plus the integral of a t dt, because remember dt got multiplied there. So taking the indefinite integral, we get x equals v naught t, because dt integrates to become t, plus 1/2 at squared, because the integral of t is 1/2 t squared. A is the constant, plus c. Now what are we going to do? We can plug in 0 in for time, and these become zeros. We find out that x is equal to c. So c really is that special constant again. It's x0, which means we have a beginning displacement listed there. So we can plug that in for c there, and we get the equation x equals v naught t plus 1/2 at squared plus x naught, or beginning displacement. Okay, now we can quickly derive our constant velocity equation here. Acceleration equals 0 when we're at constant velocity. Okay, therefore this term drops off. So x is equal to, we'll just label it v sub t, and we can add plus x naught to that also. So I get rid of the 0 on that because v is constant the entire time with constant velocity. So this would be our constant velocity equation. And a lot of times this x naught is a 0 value, but there might be some beginning displacement to add there. Okay, moving on. Our next Fab 5, the v2 squared equation. Okay, so v2 squared equals v1 squared plus 2ax. That's what we're going to try to derive here now. Okay, so here goes. Well, we know that v equals v naught plus at. Solving this for t, we get v minus v naught over a. And remember, x equals v naught t plus 1/2 at squared plus x naught. Okay, so here we go. let's plug in v minus v naught over a everywhere we see t. So x equals v naught multiplied by that v minus v naught divided by a plus 1 of a times v minus v naught over a squared plus x naught. Okay, now I'm going to take a look at this and say, well, I've got fractions I got to deal with here. So now it's just going to be a matter of rearranging until we get to our familiar form up there. First of all, take x naught to the other side. So x naught minus, or x minus x naught does equal what's left. Okay, so that's going to be our first step. Okay, then I want to start getting rid of things on the bottom here. I do see that I have an a, okay, on the bottom both sides. So I can take that a and multiply it to the other side. Okay, so a times x minus x naught equals v naught v minus v naught squared plus v minus v naught divided by 2. Okay, squared, the whole thing. Okay, now what we're going to see is just a bunch of algebra here. Okay, I am then going to multiply this out. Okay, so what I'm going to do is I'm going to common denominator this as well. So I know I'm going to need to get a 2 on top of here. This is actually 2 over 2 for this one, and I'm going to group terms together. So I will then have a 2 v naught v minus v naught squared plus, okay, let's just go ahead and FOIL this out. V squared minus 2 v naught v plus v naught squared. What does that do? It allows me to cross off these two here, and I'm left with x minus x naught times a equals minus v naught squared, okay, plus a v squared over 2. I'm going to take 2 to the other side, rearrange things, and I'm left with v squared, okay, equals v naught squared plus 2a times x minus xb, or x arrow. Okay, so that's a bunch of algebra. I kind of went quickly through that, but you can kind of get an idea. We're just subbing in and then rearranging terms to derive this. What is this v here? This is actually our final velocity after our time duration, so we can go ahead and plug that in there. So there is our familiar equation, the v2 squared equation. Okay, looking at the final Fab Five, it comes from a v average equals v, okay, plus v naught divided by 2. Okay, now integrating both sides with respect to dt, we then get our last equation, x, okay, equals 1/2 v final plus v initial times t. So imagine me putting a dt here and then a dt here. Integrating both sides, we get v times t, and then we get a times t here. V times t is actually equal to x. Okay, so this one here is our very last equation here. So this one does not have acceleration in it. Okay, so those are our Fab Five equations that we have been using all the time last year.